Good evening everyone. I am Shivani Dhok and I welcome you all for the week 7 tutorial for the course of Simulations of Communication Systems using MATLAB. So again this week's tutorial will be divided in two parts. The first part will be recap of week 7 content and second part will be the questions related to week 7 content. If you have any queries at any point of time, just pause me, just unmute yourself and you can ask your questions. So let's start with recap of week 7 content. So this week 7 content started with the concept of Markov chain, which we had left in middle in the week 6 content. So just to revisit, this Markov chain is a discrete time process, random process, and the property that, or the Markovian property that it satisfies is probability that the nth plus 1 state conditioned on or given nth state value, n minus 1th state value, and so on. So this thing is equal to probability that xn plus 1 equal to xn plus 1 given xn equal to little xn. So what does it mean? It means that nth plus 1th or xn plus 1, or in other words n plus 1th state only depends on nth state. So this is by definition. Then we looked at Chapman-Kolmogorov inequality. So it said that if we look at the transition matrix like this, so this will be equal to p to the power m into p to the power n. Then we looked at limiting probabilities. So it said that a Markov chain can have something like this. And if something like this happens, where this P is the probability transition matrix, then this pi is known as stationary distribution, or stationary, or let's say limiting. And this pi is basically eigenvector corresponding to eigenvalue 1. Then after that, we looked at what is known as accessible states. So this state says that this definition I had also covered in the last tutorial, but just for the sake of completeness, I will repeat it. So accessible state, so state J is accessible from state I if for some n in natural numbers, the nth power of probability transition matrix and its I comma jth entry is not equal to 0, which means that at the nth time instant, so there exists an n, some time instant, there exists some time instant in which the probability of going from ith state to jth state is non-zero. Okay. Then next concept that we saw was about this communicating states. So it says that two states I and j are said to communicate if I is accessible, or state I is accessible from j, and state j is accessible from state I. Okay, so this is what we call as two states are said to communicate. So which means that we can move from at a particular time instant, or where this probability transition matrix is nth power I comma jth entry is non-zero. And that point, if suppose this pij is non-zero as well as pji is non-zero, then we can say that I is accessible from state j. So we can move from state I to we can go from state j to state I, and also we can go from state I to state j. So from I and j should be accessible from each other. And if that is happening, then such a state is known as, or such two states are said to communicate. And then the last concept that we saw for Markov chain. So this was just stated. Don't worry too much about all of these things, I think. So for this, we defined a so for transient and recurrent states, we defined a probability Fi. So this thing is basically your probability that if we start from ith state, we will get back to ith state again in some n, or at some n, at some time instant. And based on the value of this Fi, so if this Fi is 1, then the ith state is recurrent, and if this Fi is less than 1, this ith state is transient. Okay, so these are the two things that we had seen, or two additional definitions that we saw for Markov chains. So for now, we are not using this Markov chains right now, but we will use it in the later stages. And then after this particular thing, we started with another concept, that is information sources and their how to process them. So first we started with information sources, and then we said that there are multiple types of information sources, in which there is text, then there is speech, then we have images, and then we have videos. So if we observe carefully, all of these are information signals, and these might be of our interest for communication. So this text is anyway we are typing, so it will, so the whatever communication setup or whatever user interface we are using, that will take care of it. However, these signals, speech, images, and videos, naturally they are analog in nature. So these are analog signals, and the problem with this analog signals is we can't do digital processing in our systems. Why? Because we have precision issues and memory issues. So this analog signal, if you consider, will have infinite precision. So it can even store, like this analog signal can have 10.0000000001 like that. However, my computer can't store this much amount of decimal point. It will say that it's okay, okay, it's just 12. So this analog this kind of analog we can't process. Similarly, if we are not sampling or if we don't have discrete time signals, then at each time instant, maybe it's 1.1, or suppose I have 1 second and 2 seconds, there will be some signal present here also, maybe here. So whatever time instant you take, let's say here, you'll have some signal value. Similarly, if you take here, you will have some signal value. So which means that between 1 second and 2 seconds there are infinite values. So I have a limited amount of memory, I can't store these infinite values, and therefore we want this analog signals to be converted to digital. So due to memory issues, due to memory and precision issues, we can't process them. Which means you need to convert them to digital. And what does digital mean? Digital means two things. It should be discrete in time and discrete in amplitude. Okay, and this analog to digital conversion, that is this ADC. This ADC is basically, let me change the color. This is basically analog to digital conversion. And this involves these three steps. That is sampling. So what does sampling do? So this sampling will basically convert continuous amplitude, continuous time plus continuous amplitude to discrete time and continuous amplitude. So this is what sampling will do. This quantization will basically convert this discrete time continuous amplitude to discrete time discrete amplitude. And after that we have source coding. So basically this source coding will helps in compression. So why do we need to do compression? We want to use our memory or communication resources efficiently. Okay. So let us first start with sampling. So let's take the ideal sampling case, simple one. So this ideal sampling case simply means that it's just multiplication by impulses and all those standard things. I won't go into detail of all of these things for now, because anyway this is a part of signals and systems course, but still as an important concept I'll state Nyquist sampling theorem. So We have this Nyquist sampling theorem. So what it says is a band limited signal can be uniquely reconstructed from its samples if the sampling frequency is at least twice the maximum frequency in the signal. So we have a band limited signal. Let's say this is its frequency response. We have 0 here. We have this maximum frequency minus, or let's take the notation that we had taken. So this is B, this is minus B. So the sampling frequency Fs should be greater than or equal to 2 times B. So this is also, this is your B, and this can also be, for band limited signal we can call this as a bandwidth. So the sampling should be twice its bandwidth. Okay. Okay, so we have this thing here. After that, we looked at what is known as quantization. I won't go into detail in the interest of time. I'll just mention what all things we did. So in quantization, we looked at three things. First one was a simple Lloyd max quantizer. So basically this minimized the mean square error, and we had to iteratively look at the thresholds and the range over which we will be minimizing. So there it is an optimization problem that we need to solve iteratively. Next thing that we looked at was extension of this Lloyd max quantizer for for vectors, and that is k-means algorithm. And after that we looked at what is known as uniform quantizer. I'll take few questions on this uniform quantizer today. Okay. And then the last thing that is left is this source coding, and this shall be covered in next week. So that's all about the recap. If you have any questions, then let me know. Otherwise, I'll move on to the solving part. Okay, if there are no questions, then let me move on to the questions part. So like every week, this solving part will be a mixture of past year assignment questions and some additional questions that I have prepared. So let's start with the first question. So this says that a Markov chain is a discrete valued random process. Markov chain is a discrete valued random process where the probability of the process being in state I at time n plus 1 depends on the state, and we have four options. So the first option is at time index n, second option is at all the past time index, third option is at time index n and n minus 1, and last option is it does not depend on the past time indices. So by definition of Markov chain that we have been looking, the correct answer is the first option. We have discussed it today also at the beginning of the session. Still, I repeat it. So this is the correct option by definition. And still, I'll repeat the property what we discussed. So probability that n plus 1th state is at state I given all the previous states this is equal to probability that the n plus 1th state is I given nth state is xn. So this all the past values have nothing to do with whatever is happening at this particular instant. It only depends on the one previous instant. So this is by definition, and therefore the correct option is option 1. I hope there are no queries in this part. Okay, let me move on to the next part. So the second question says, consider Markov chain that has n states. So what we are given is one, we have number of states. Number of states is n. Then we are given probability transition matrix. So we have probability transition matrix that is equal to P, and this P, the I comma jth entry of this is basically equal to probability that xn plus 1 is j given xn equal to I, and we can say that it is Pij, little Pij. Okay, then what is given to us is, suppose Pn is a vector consisting of probabilities of each state as at nth time instant. So what does this vector say? So this vector Pn is basically a vector that has these entries. Probability that xn equal to state 1, probability that xn equal to state 2, and so on. Probability that xn equal to state n. Okay, so this is the probability of each state, or probability at nth time instant, or probability of each state at nth time instant. Now what is asked to us is find Pn plus 1. So this is the first part that we need to do. And then it is said that if initial probabilities, sorry, this is the first part that we need to do. And then it is asked is, if P0 is the initial probabilities of each state, then reduce Pn plus 1 in terms of P0 and P. So let's first start with this Pn plus 1. So what do we mean by Pn plus 1? So this Pn plus 1 vector is basically a vector that has probability that x1 is equal to 1, probability that x2 is, sorry, xn plus 1 equal to 1, probability that xn plus 1 equal to 2, and so on till probability that xn plus 1 equal to n. Okay, And we know that this is a Markov chain. And therefore, the n plus 1th instant state will only depend on what happened at nth state. So what we'll do is we'll generalize it and we'll say let us try to compute probability that xn plus 1 has take state j. What is the probability given we know Pn? So this vector is given to us. So consider this given to us. So using this, we need to figure out what is probability that at n plus 1th state or at n plus 1th time instant, we are at state j. Okay, so what we can do is we can write this x j to probability that xn plus 1 is j given xn is 1, or we can use law of total probability. Xn takes state I into probability that xn has taken state I. And how many values can I take? I can take values from 1 to n. Okay, and this from your probability transition matrix, probability that xn plus 1 equal to j given xn equal to I is simply your I comma jth entry from your probability transition matrix. So this is like this. So what we have now is summation I equal to 1 to n, probability that xn equal to I into Pij. So how can we write this? So this thing we can write as P1j into probability that xn equal to 1 plus P2j into probability that xn equal to 2 plus so on Pnj into probability that xn equal to n. Okay, now let us try to stack all of these in a matrix form. So let us take this and write it in this form. Probability that xn plus 1 equal to, or what I'll do, I'll just copy paste this also. And what is this? This is simply probability that xn plus 1 equal to j. And this j can again take values from 1 to capital N. So let me stack these values. We add an intermediate stage here. Equal to some matrix. So we have a linear combination here. So we can have some matrix coming into picture. Multiplied by probability that xn equal to 1, probability that xn equal to 2, so on till probability that xn equal to I, so on till probability that xn equal to capital N. Okay, so now what happens is let's focus on what we know. So this probability, we know this part, this thing. So let me just, this will correspond to this row multiplication here. Okay, so you do matrix multiplication row into column like this. So let us focus on this jth row. So this is my jth row. So let us focus on that. So this the first element here will get multiplied by probability of xn equal to 1. And what gets multiplied by it? It's p1j. Then what we have here is next term is p2j into probability of xn equal to 2. So this is p probability of xn equal to 2, and the second entry here will get multiplied by this thing. So here we will have p2j, and so on. We'll have here the last entry. So this gets multiplied by probability of xn equal to capital N. So this thing here will be probability of nj. So now this j can take any value from 1 to capital N. So just repeat, let us try to repeat the same thing for j equal to 1 and j equal to 2. So for j equal to 1, we just need to take this row, whatever we have written here, and replace j by 1. So we will have probability of 1 1, then probability of 2 1, and so on till probability of n2. N1. Okay. Let us add additional term here. Probability of ij. So we'll have I1 here. Okay. Then we'll have probability of 2 2, probability of, sorry, 1 2, probability of 2 2, then so on, probability of I2, and so on till probability of N2. Okay, so this will be probability of Ij, and so on. What we will have here will be probability of 1n, probability of 2n, and so on till probability of in, probability of, or p of nn. Okay, now if you observe carefully, my probability transition matrix was something like this: p11, p12, and so on till p1n. Then we'll have p21, p22, and so on till p2n, and so on till pn1, pn2, and so on till pnn. So this is our probability transition matrix. And if you observe carefully, this matrix here, whatever we are having, is basically transpose of this probability transition matrix. So what we have here is this matrix is basically p to the power, p transpose. Then this matrix, whatever we have, or this vector, whatever we have, is basically pn plus 1. And this vector, what we have is basically, this is pn. And this vector, whatever we have here, is pn plus 1. So therefore, the relation that we have now, so therefore, we get pn plus 1 vector is p transpose pn. Okay, so this is the first part. So this is the answer for the first part. If you have any questions, just let me know. Okay. If there are no questions here, then let's move on to the second part of this question. So it says that if P naught is the initial probabilities of each state, it is the prior probabilities. Then reduce Pn plus 1 in terms of P naught. So from this recurrent relation that we have, so using the relation in 1, we can write P1 as P transpose P0. Then we can write P2 as P transpose P1 vector, and P1 we can substitute as P transpose into P0. So this comes out to be equal to P transpose square into P0. Then what we can do is P3 will be equal to P transpose P2, which will be equal to, so we can substitute this P2 as P transpose square. So what we get is, or we can also write this as P square transpose. So what we'll get is P transpose to the power 3 into P0. And if we generalize this, then this Pn plus 1 can be written as P transpose Pn, which comes out to be equal to P transpose to the power n plus 1 into P0. Okay, so this is how we can write the n plus 1th state probabilities with the help of the initial priors and the transition or the probability transition matrix. Is it clear? Any questions? Okay, if there are no questions, then let me quickly move on to the next question. So here is the next question. So what it says is, suppose you have an RGB image of size 512 cross 512 and each pixel is quantized using 8 bits. So what it says is, first thing, RGB image of dimensions 512 cross 512. And each pixel is quantized using 8 bits. So what we need to figure out is what is the file size of the image before compression, and another thing that we need to figure out is if I want to transmit this image using using 50 kbps, how much time will how much time we shall require. So okay, so first of all I want to show you something using MATLAB. So for that I'll share MATLAB screen. Just a minute. Okay. I hope my screen is visible. Okay, so now what I'll do is I've created some example. So this is what I am calling, this is test image example. So this is peppers.png is a text image that MATLAB MATLAB inbuilt has. So for that, what I'll do, let me just load this image. So I am read. So this I am read loads the image, and this I am show command, this displays the image. Okay, so if I run this, so this is the image that we are having here. Okay, so this is the peppers image that we have inbuilt. So okay, let me do some minor changes. Fine. So this is what we are having. So this is the first figure that we are having here. Okay. Now if you observe carefully, this image has a dimension. This image that we have just loaded, this image has a dimension of, okay, oh sorry, just a minute. I think now it should be visible. So this is the pepper image that MATLAB inbuilt has, like this. So I am read will help me to load, and then I'll have this image that we are having here. Okay, so this is what we call as Pepper's image, and if you observe carefully, this is of the dimension of 384 cross 512 cross 3. So each of this particular thing, or each of 384 cross 512, we have three levels or three matrices stacked one below the other, each of dimension 384 cross 512. So what does these each of these entries or each of these matrices correspond to are the pixel values for three colors, that is red, green and blue, RG and V. That's why this is known as an RGB image. So let us try to see if that is true. So what I'll do is I'll try to plot the first level, all rows and all columns of the first level of the image. So I'm getting something like this. Okay, let me do it properly. Okay, so okay, fine. For now it's okay. I'll change the things. So this is a gray image. If I run it this way, it will be a gray image. Let me do one thing. For now, let me just do this. Okay, fine. So if I run this, I'll have this image coming up here. So you can observe that this is the first plane that I'm plotting, but it's still showing as gray. Same thing I can do with second plane. Again, it is showing gray, but it is a little bit different. So if I see the first one and if I see the second one, simultaneously. These two are different images, so something is different in both of them that we are not able to figure out what. And then we have the third part. Again, there is something here, but we are not able to understand what difference it is making. Third level. Now what I'll do is, I claim that these three correspond to the red, green and blue part of the image. Okay. So in order to visualize that, what we'll do is, we'll take zeros and first, so suppose I have the first depth, then I'll only make the first depth as non-zero and rest all will be zeros. Similarly, if I want to visualize the green part, then I'll do second row, second depth as non-zero and take the values of corresponding to that image as non-zero part. And similarly for blue, I can do the same thing. So what I'll do is, I'll quickly run this, and then if you can see, we have something like this. So the first figure that we generated was R, so this corresponds to the red part. Then we have green, this corresponds to the green part in the RGB image, and then we have this blue, this corresponds to the blue part. So what I mean to tell here is that all of these planes, like all of these, this image corresponds to one color. Now if I look at, let's say I11 is I all rows, all columns in first one, and if I try to visualize this particular variable, so if you observe carefully, this is having lot of values which are similar in nature, but the maximum value it can take is 255, and this 255 basically corresponds to the maximum value that it can take. And another thing that you can note here is, you can see the values that are located, let's say in this part, all are 25, which means all are same, which means that this image is having highly correlated data, and that will be the case in all the possible or all the images. So right now what I want to say is, each of this matrix that is there in all of these three levels, in each level, for each matrix we have pixel values, or each of this entry, let's say this is a pixel, each of this entry can be represented using 0 to 255 values, and this can be represented using 8 bits. So what it means is, if I have a 384 cross 512 dimensional 3D or RGB image, so it will have three planes, each corresponding to red, green and blue, and in each of this red, green and blue image, each entry in this matrix can be represented or is represented using 8 bits. Okay, so let me stop. Oh, okay, let's do it here only. So what question we had was, let me open, so it has a long calculations. So for that, just we'll write a code. Okay, so what it said is, we have, so let me repeat the question. We have RGB image of dimensions 512 cross 512. What does this imply? It means that we have three matrices of dimension 512 cross 512. Each entry in this or in these three matrices can be represented using 8 bits. These are 8 unsigned bits. So if you can see here, the type or the data type here is unsigned 8. So what we'll do is, first thing that we will figure out is total number of pixels, and that is equal to 512 cross 512 cross 3. Why do we have 3? 3 means R, G and B. Then we can have number of bits required. So that will be equal to total number of pixels into number of bits required to represent each bit, and that is 8. Since 8 bits per pixel. Okay. So what are the total number of bits required? Let's run it and see. So this is question number 3 in tutorial 7. Okay. So the total number of bits required here, so I'll just write it here. Is this huge? Okay, this is uncompressed data. Okay, this is uncompressed data. This is the number of bits. Then what is given to us is, so this is not all, this is what is asked to us is, so this is the file size. These many number of bits are required to save this particular size if we don't compress. So that is 629145 So just for fun, what we'll do, we'll divide it by 8. So this will give me bytes, and then we can just multiply it by 1024. That will give me kilobytes, and then we can again multiply it by 1024 to get megabytes. So this is around 0.75 megabyte image, raw image. Or in other words, we can simply keep it in kilobytes. So it's 768 kilobytes. So it's a huge image. Our images are not of this size. It's in kbps. This is a very huge uncompressed image. So we have seen that already the image was highly correlated. So we can do some techniques to reduce this size by compression. Okay, but for now we have this thing here, and then what is given to us is, we are given transmission rate of 50 kilobits per second. This is given to us. So time for transmission, okay, let me write it. Let me just define this first. TX rate is 50 kilobits per second. So 50 into 1024 per second, and time for transmission will be equal to number of bits required to transmit, or we need to transmit, divided by transmission rate. And if we do that, the transmission rate comes out to be equal to 51200 seconds, which is too high. Again, the transmission rate will be higher, but still this 51200, we are just sending the image for ages now. So this is now how we do it. So this is a raw example. This is now how we do it. So what I'll do now is, okay, just a minute. Okay, so this is what we are having right now. What I'll do, I'll take screenshot of this. And paste it in whatever we are doing. So that it comes in your notes. Okay, so that's all for this question. If you have any queries, then let me know. Otherwise, I'll move on. Okay, so let me stop sharing. Let me start sharing from my tab. Okay, so this is what we were having. Let's see if it is okay. So this is what we had. So this is the solution that we just saw in our result. So this was the code, and there is some solution that is absent from here. I'll add it in the notes, but you can just copy or replicate this code and generate your own answers. Any questions in this part? So what is happening here? So I'll just write some key observations. Key observations here which will motivate for future lectures. So first thing, this is uncompressed image. This has very high size or very high file size, and it takes lot of time to transmit. Then we saw high correlation in image data, and again this image data, high correlation in this image data, and this same thing happens, or we have similar observations even for voice and image videos. So all of these are highly correlated data, and we can exploit this correlation to reduce file size and user resources in a better way, and this is done by compression, which we will see in the next week, coming week. Is it clear till this point? Okay. Okay, if this is clear, then let me move on to the next question. This is just an information question. I hope that this will be covered in the coming week. This was there in last year's assignment, but it was not covered in videos. Still, I added this question in case something similar comes in this week's assignment. I haven't seen this week's assignment yet. Okay, so this is related to JPEG compression standard, and this JPEG compression standard is for images. And this JPEG stands for Joint Photographic Experts Group. So this JPEG stands for Joint Photographic Experts Group. That corresponds to your JPEG. And this is a very lossy compression technique for images. So this JPEG, very lossy. So if you have a PNG image and if you have a JPEG image, PNG image will have a better quality compared to your JPEG images. This is very lossy. So if you zoom a PNG image and if you zoom a JPEG image, you can clearly see the difference between both of them. Okay, and another thing is all of these image processing techniques or compression techniques for images, they generally use transforms. And the transform technique that this particular JPEG compression standard uses is discrete cosine transform. So this JPEG, this I'm giving just a piece of information. JPEG uses discrete cosine transform as transformation technique. Okay. So the correct option here is discrete cosine transform. This was there in last year's assignment, but was not covered in videos. So still I took it in case something similar comes up. So just a piece of information. I hope there are no doubts in this part or till this point. If there are, please let me know. Otherwise, I'll move on to the next question. Okay. Okay, so let's start with question number 5. So it says that a uniform quantizer with step size delta. For a uniform quantizer, we have a uniform quantizer with step size delta. Find the mean and second moment of the quantization error. So we want to find mean and second moment of the quantization. So what is mean? We know, and what is second moment? That also we have seen earlier. Just for the sake of completeness, let me write it. For a random variable x, its mean is expectation of x, which is integral. So here let's consider continuous distribution x into fx of x dx, where fx is pdf of continuous random variable and its second moment expectation of x square is equal to integral x square fx of x dx. So and its second moment, what am I writing, comes out to be something like this. So what we need to find is, we need to find mean and second moment of the quantization error or your quantization noise. Both are same. In the lectures we have referred it to quantization noise. Okay, so let's start to do it. But before that, let us understand what kind of random variable is this quantization noise. So the first question that should arise in our mind is what kind of or what distribution does quantization error let's say it is denoted by capital E follow. So this is the first question that we should think about because we want its PDF to figure out what is its mean and second moment. Okay. So this is the first question. So to answer this, what we'll do is, let us first try to understand what does this particular quantization thing does. So what it will do is, let's say we have a signal with some value x min and some value x max. And what is told to us is we want to quantize it with a step size delta. So let's say we have something like this. So after every deltas, we'll have a sample, or we'll have an interval, something like this. Like this we will have, and then we'll have some thresholds. So A0, A1, A2, A3, A4, A5, A6, A7, and A7. So these are your quantization levels, or in other words, these are your quantization levels. So whatever comes in this particular interval, so suppose I get some value. So okay, let me just draw it. We draw some random signal, something like this. Okay, so whatever comes, or okay, it will be a discrete time signal, so let it be something like this. Stick it here. Okay, so this particular point is here, so it is lying in this interval. So what you will do, you will map it to this point, A4. Similarly, you have something here. Now this lies in this interval, so you'll map this to, sorry, so it lies in this interval, so you'll map it here. Similarly, you have a point here which lies in this particular interval, so you'll map it to A6 and so on. So what in principle is happening is, you have a lower limit and you have an upper limit, and then you have a quantization level AI. So anything that falls in this particular interval, so any point in this interval will be mapped to AI. And what is given to us is, we are given the step size. So the step size is this delta. So this is your delta, and this is a uniform quantizer. So what happens is, this AI is basically midpoint of the interval Li to Ui. So what does it mean? You have a delta by 2 in a distance here, and another delta by 2 distance here. Okay, so you have it something like this. So basically this particular point is your delta by 2, and this particular point is your delta by. Okay, so something like this we are having right now. Okay. Just a minute. So sorry, just a minute. Okay, yeah, fine. So we have something like this. So what you can do is you can write this ui as ai plus delta by 2 and you can write this li as ai minus delta by 2. So in other words, what you can say is any point that lie between these two. So therefore any point that lies in ai minus delta by 2 to ai plus delta by 2 will be mapped to ai. So your quantization error E will be equal to your xi minus ai. So if it lies in that particular thing, and this xi belongs to ai minus delta by 2 to ai plus delta by 2. And then if you do this, then this, like if you subtract, so what we have here is your xi. Okay, let me write it. So if you subtract this ai from this particular interval, then you can say that this e or this e will be from minus delta by 2 to delta by 2. So what is, or let's take it in this way. Okay, upper limit will be mapped to below 1. Okay, so now what is happening is, if you, so you are here, you are mapping any value here. So if you are at this particular point, your quantization error will be this point value minus ai. So it will be positive. And this particular thing here is ai plus delta by 2, and this is the maximum thing that you can map to. So your quantization error, if you have ui and you're mapping it to ai, will be equal to delta by 2. Similarly, if you are just above this li, that is just very close, just little bit more than ai minus delta by 2, and still you will be mapping it to ai, which means that this ai minus delta by 2 minus ai, that is your xi minus ai, will have a value which is very close to minus delta by 2. Now your value, your point xi can lie anywhere between these two values. You can have any value here, or you can pick up any value here uniformly, which means that the error that you can come up or that you will get in this particular quantization interval can take any value uniformly from minus delta by 2 to delta by 2. So therefore uniformly, so all with same probability you can take, or with same probability density, and this is a continuous random variable. So therefore your E error is uniformly distributed in interval minus delta by 2 to delta by 2. Therefore your PDF AFE of E will be equal to 1 if E belongs to minus delta by 2 to delta by 2. It is 0 otherwise. So now we know the distribution. Now we can figure out the mean and variance of this thing. So therefore, first thing that we need to find out is mean of this. So mean of this error is equal to integral. The limits are from minus delta by 2 to delta by 2. Otherwise, your PDF will be 0. So minus delta by 2 to delta by 2 E into, I'm sorry, this is 1 by delta. E into FE of E dE. This comes out to be equal to integral minus delta by 2 to delta by 2 E into 1 by delta into dE. So This delta is constant, we can take it outside. 1 by delta integral minus delta by 2 to delta by 2 into e dE. This is an odd function, and integrating an odd function from minus a to a, which means that this comes out to be equal to 0. So your expectation or expectation of your error comes out to be equal to 0. Now similarly, we can find out the second moment, that is expectation of e square, and this will be given by integral minus delta by 2 to delta by 2 e square into 1 by delta and into dE, and this comes out to be equal to e cube by 3 delta, and need to be integrated by from minus delta by 2 to delta by 2. And if we do that, what we will get is delta by 2 cube minus delta by 2 cube upon 3 delta. This comes out to be equal to 2 times delta cube by 3 into 2 to the power 3 delta. This 2 gets cancelled and 1 delta also gets cancelled. So we will have delta square by 3 into 2 square, which comes out to be equal to delta square by 12. So what we have obtained now, this is the second moment. So what we have obtained now is your expectation of E is 0, which is your mean, and expectation of E square is equal to delta square by 12. This is your second moment. Where delta is your step size. I hope it's clear. If you have any questions, please ask. Okay, if you have no questions, then let me quickly move on to the next question. Okay, so this question says that suppose you want to quantize a sinusoid with peak to peak value as 1 volt. So what is given to us is we have a sinusoid with peak to peak value as 1 volt using n bits. Find the number of quantization levels and step size. And we need to specialize our answer for n equal to 3. Okay, so what is given to us is we have a sinusoid. And this is the peak value and this is the valley. So this peak to peak, whatever we have, this is 1 volt. And what we need to find is, and what is given to us is this sinusoid is quantized using n bits. So therefore, the number of quantization levels L is given by 2 to the power n, that is 2 to the power number of bits. And if I'm having L levels and I need to take care of this much duration or this much interval of 1 volt, or in general step size delta is given by x max minus x min divided by L. And here this particular thing that is given to us here is basically, or x max minus x min corresponds to peak voltage in our given question. So this x max minus x min is given to us as 1 volt, and therefore this you can simply substitute as 1 divided by, so this is exactly what we have been given. This is your peak to peak voltage, and then this is equal to 1. That's what we substituted, and the number of levels that you have now is 2 to the power n. So you have the step size delta comes out to be equal to 2 to the power n. And what is told to us is we need to specialize this result for n equal to 3. So if number of bits is equal to 3, which is equal to n, therefore L comes out to be equal to 2 to the power 3, which is 8 levels, and therefore delta comes out to be equal to 2 to the power minus 3, which is 0.125. So this is your step size. Okay, this is a simple question, but still, if you have any questions, then let me know. Okay, if there are no questions, then let's move on to the next question. So what it says is find the quantization noise variance in the previous question. So we have seen this. So this quantization noise is equal to your quantization error. Okay, and what we need to do is we need to find variance of E, where this E is quantization noise. And in general, the variance can be written as second moment minus square of first moment, that is mean. So this is a standard formula that you can look at. Okay, so this we have, and if you observe carefully, these two things we have found out in one question before this, that is in question number 5. So we have figured this out, we found out these. So if you refer to question 5, expectation of E was equal to 0. So we had expectation of E, sorry, to write E here. Yeah, expectation of E we had obtained as 0, and the second moment expectation of E square we had obtained as delta square by 12, where delta is step size. So therefore variance of E comes out to be equal to delta square by 12 minus 0 square, which comes out to be equal to delta square by 12. And for n equal to 3, like in question 6, we have asked to specialize your answer for n equal to 3. So if n is equal to 3, then variance of E comes out to be equal to, so we had delta as 2 to the power minus 3, that is 0.125. So this came out to be equal, this will come out to be equal to 0.125 square by 12. And if you solve this thing comes out to be equal to, or let's say approximately equal to 1.3 into 10 to the power minus 3. So this is the quantization error that we will get. You can use your calculators to figure this out. Any questions? Okay, if there are no questions, then let's move on to the 8th question now. So now I'll take two questions on sampling rate, two questions on sampling and one question sampling plus quantization mix. So here is the first question on sampling. So it says that let xt is sine square 2 pi f naught t, and we need to find out the minimum sampling frequency. So what is given to us is xt, which is sine square 2 pi f naught t, and we need to figure out what is the minimum sampling frequency. So this minimum sampling frequency fs is equal to 2 times fm, where fm is maximum frequency in that signal, in the signal. Okay, so this is the signal that is given to us, and this is in sine square form. So let us try to simplify this. This comes out to be equal to 1 minus cos of 2 times 2 pi f naught t by 2. So what we have used here is a simple trigonometric identity, that 1 minus sine square theta is, sorry, 1 minus cos square theta is 2 sine square, 2 sine 2 theta. What am I writing? 1 second. 1 minus cos 2 theta is 2 times sine square theta. So this identity we know, and using this identity we have figured it out, and now we can rearrange this particular thing here, the angle of this. So we can write it as 1 minus cos of 2 pi 2 times f naught t by 2. Okay, so how will this, so if you observe carefully here, this thing, this is a DC component, means zero frequency, and this part here, this is a single tone sinusoid with frequency 2 times f naught. So therefore maximum frequency that is Fm comes out to be equal to 2 f naught, and therefore sampling rate or Fs comes out to be equal to, or minimum sampling rate comes out to be equal to 2 times Fm, that is equal to 2 times 2 f naught, which comes out to be equal to 4 f naught. Okay, so this is the maximum frequency that we have obtained here. Sorry, minimum sampling frequency that we have obtained. So this is basically your minimum sampling frequency. Okay. Any questions? This is simple thing. We have already seen in signals and systems course, but still. Okay. If you don't have any questions here, I'll move on to the next part. So this is question number 9. This has two parts. So it says that if x1t and x2t have Nyquist sampling rate, what do you mean by Nyquist sampling rate? It means the minimum sampling rate. Nyquist sampling rate of fs1. So x1t has sampling rate of fs1, minimum sampling rate of fs1, and x2t has minimum sampling rate of fs2. And then we need to find the Nyquist sampling rate of these two quantities. So what is given to us is x1 of t has Nyquist sampling rate fs1, which means that the maximum frequency, so this is maximum frequency in x1t, comes out to be equal to fs1 by 2. Similarly, x2t has Nyquist sampling rate as fs2, which means that fm2, which is the maximum frequency in x2t, is equal to fs2 by 2. So this is given to us. So this Nyquist sampling theorem is anyway for a band limited signal, and therefore this is what we are having here. Okay, so now what we need to do is we need to find out the Nyquist sampling rate of, first thing, y1 of t, which is convolution of x1t and x2t, and second thing is y2 of t, which is multiplication of x1t and x2t. Okay, so let's start with the first part. So first part is x1t convolved with x2t. So in time domain, we are not able to understand anything. So best thing is to go to frequency domain. So what we will do is we'll take the Fourier transform. So we'll take the continuous time Fourier transform. So we'll have y1f that comes out to be equal to x1 of f multiplied by x2 of f. So we are using the property convolution in time implies multiplication in frequency. Okay. So now let us assume some certain things. So let's say that this x1 of f takes something like this. This we know, and this x2 of f has spectrum something like this. This is x1 of f, this is x2 of f, and what we want is we want to multiply these two to get y1 of f. Okay, so we'll have two cases. First one, when fs1 is greater than fs2, let's say equal to fs2, greater than or equal to fs2. So what will happen is we have this axis here, we'll have this fs1 x1, so we'll have this fs1 by 2 and minus fs1 by 2, and then on the top of it we'll have to multiply something like this. So this thing here is your x1 of f, and this red part here is your x2 of f, and if you want to multiply both of them, then this is the only region, and okay, let me write it, fs2 by 2 minus fs2 by 2. So this grain is the only region in which your multiplication will be non-zero, because here your x2 of f is 0. So here your signal will lie between minus fs2 by 2 to fs2 by 2. Okay, and suppose opposite thing happens, that is fs2 is greater than fs1, In that situation, we have something like this. We have fs1 by 2 minus fs1 by 2, and then we have something like this. So this is your x2 of f. So this is fs2 by 2. This is minus fs2 by 2. And again the non-zero, after multiplication, this is the non-zero region. So this particular thing here is non-zero. So then what we will have here is minus fs1 by 2 to fs1 by 2, like this. So what we observe here is y1 of f will be non-zero, or let's say maximum frequency in y1 of f, let's say it is fm, is equal to fs2 by 2 if f1 is greater than or equal to f2, fs1 is greater than or equal to fs2. It is equal to fs1 by 2 if fs1 is greater than fs2. Sorry, less than. So this, what we can do is we can simplify it and write as, so therefore here fm, so here it is fs2 by 2 and you have minimum value as fs2. Similarly fs1, so here the minimum is fs1. So this fm you can write as half of minimum of fs1 comma fs2, and therefore minimum sampling rate which is fs, which is equal to 2 times fm, comes out to be equal to 2 times half of minimum of fs1 comma fs2. So this comes out to be equal to minimum of fs1 comma fs2. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the second part of the same question. So in second part, so this was the first part, this we have done. The second part says y2 equal to x1t into x2t. So this is the second part. y2t equal to x1t into x2t. So therefore your y2 of f will be equal to 1 upon 2 pi into x1 of f convolved with x2 of f. So now opposite thing will happen. So multiplication in time domain will lead to convolution in frequency. Now there is a standard trick here. So if I have two signals, let's say x1 of z1 of f and z2 of f, and let's say z1 of f is between a1 to a2 and this is between b1 to b2, then z1 of f convolved with z2 of f, this will lie between a1 minus a2 a1 plus a2 to b1 plus b2. Okay, you can check your signals and systems course. I won't get into derivation or of this particular property, but this is what happens here. And now what we are having is this y2 of f is equal to 1 over 2 pi x1 of f convolved with x2 of f. We know that this x1 of f lies between minus fs1 by 2 to fs1 by 2, and this x2 of f, this lies between minus fs2 by 2 to fs2 by 2. This we know. So therefore, by using this particular property which I just stated, this y2 of f will lie between minus fs1 by 2 to plus minus fs2 by 2 to fs1 by 2 plus fs2 by 2, okay, which we can equivalently write as minus of fs1 plus fs2 by 2 to fs1 plus fs2 by 2. So what we observe here is the maximum frequency in y2 of t, which is fm, comes out to be equal to fs1 plus fs2 by 2, and therefore sampling frequency that is fs, which is 2 times fm, this comes out to be equal to 2 times fs1 plus fs2 by 2, which is equal to fs1 plus fs. Is it clear? Any questions at this point? Okay, if you don't have any questions, let me move on to the last question for today. So it's a mixture of sampling and quantization kind of questions. So it says that consider a voice signal with maximum frequency as 3.5 kilohertz. Suppose it is sampled with a sampling frequency of 8 kilohertz. Okay, so what is given to us is, first we have a voice signal, or let's say given a voice signal, and this is sampled at fs equal to 8 kilohertz. Then, so what does we mean by sampled at 8 kilohertz? It means that, let me use another color. It implies that at each second, or in 1 second, we get 8,000 samples of voice signal. Then it is given to us is each sample is uniformly quantized. Each sample is uniformly quantized to 8 quantization levels. So each sample quantized to one of the 8, let's say L equal to 8 quantization levels. Which means number of bits required to quantize this n is log L to the base 2, that is log 8 to the base 2. We can write this as log 2 to the power 3 to the base 2, which comes out to be equal to 3. Okay, so what we have till now, we have a voice signal in which at 1 second we get 8,000 samples, and each of these 8,000 samples are quantized to n bits. Now what we are asked is, we need to figure out what is the data rate in bits per second. Okay, so what we have till now is, so from here, from the first point, or let me just number it, this is 1 and this is 2. So we have from 1 we get 8,000 samples per second, and from point 2, that is from this particular point, we get, or each sample is represented by 3 bits. Okay, so therefore the data rate is number of samples per second multiplied by number of bits required per sample. So this will give me number of bits per second. Okay, so now what I have here is, your number of samples are per second are 8,000 samples per second multiplied by, you have 3 bits per sample. So that comes out to be equal to 24,000 bits per second, which is approximately equal to 24 kilobits per second. So it's generally 1024, but if we take it around, which is close to 1000, so this comes out to be equal to around 24 kilobits per second. Any questions? This was also a simple question. If you have any questions at this point, then let me know. This was all I had to cover today. If you have any questions, feel free to ask. If you have any questions in today's entire tutorial, please feel free to ask. If you have no further questions, you are free to leave the meeting. Thank you for attending today's session.